Welcome to This Explainer. I am honestly so thrilled to guide you through today's topic because we're going to completely flip the way you look at the world around you. We so often think of the natural world as just, a beautiful backdrop to our lives, a place to go for a hike or take some great photos. But what if I told you it's actually humanity's most advanced, ancient, and rigorously tested R&D laboratory? Today, we're exploring biomimetics and bioinspiration. It's the incredible science of looking at nature to find the blueprints for our absolute most cutting-edge technologies. Okay, let's dive right into this. Take this magnificent bird, the kingfisher. It's famous for plunging into the water to catch fish with barely even a ripple. It's beautiful, sure, but what on earth does a bird diving for its lunch have to do with modern engineering? Well, as we'll see in just a bit, the aerodynamic genius of this specific splashless dive actually solved a massive billion-dollar modern engineering crisis.
But the kingfisher is really just one single example. Our planet is currently home to roughly 11 million species. I want you to really let that number sink in for a second. 11 million. In the world of biomimetics, we don't just see 11 million animals or plants, we see 11 million patented, field-tested solutions to some of the most complex structural, chemical, and aerodynamic problems on Earth.
Which brings us to the central question of this explainer. How can we learn from nature? Notice the phrasing there. The goal here is a total mindset shift. We're moving away from simply looking at nature and stepping into a world where we actively learn from it. So, here's our roadmap for today. First, nature's laboratory. Then, key concepts and terms. From there, inspiration and practice, levels of application, innovation methods, and we'll wrap up with the bio-inspired future. Let's kick things off with Section 1, Nature's Laboratory. The magic word for today is biomimetics. It actually comes from the Greek words bios, meaning life, and mimesis, meaning to imitate. But I want to be super clear right up front. This isn't just about making things look organic or pretty. Biomimetics is the rigorous study and actual replication of natural processes to solve very real human challenges. Moving right along to Section 2, Key Concepts and Terms.
Now, what's really interesting here is breaking down the different ways we use nature in design. We have biomimicism, which is purely aesthetic, like a building designed to merely look like a flower. But then we have bionics, which is the actual integration of biology and engineering. And of course, biomimetics, which treats nature as a model, a measure, and a mentor. It's the absolutely crucial difference between designing something that just looks like a flower and designing a technology that actually functions like one. And that brings up a massive paradigm shift, captured perfectly by this quote. Nature cannot be summarily copied. You see, we can't just copy-paste biology directly into our technology. I mean, a bird flaps its wings, an airplane doesn't, right? Instead, we have to treat nature as a mentor, not just a model. We have to observe, understand, and then translate nature's underlying principles into our own materials.
All right, Section 3, Inspiration in Practice. Remember that kingfisher from the beginning? Well, back in 1997, Japan's high-speed Shinkansen bullet train had a massive problem. When the train exited tunnels at ultra-high speeds, it pushed this huge wave of air out in front of it, creating a sonic boom that was an absolute nightmare for local residents. The lead engineer, Eiji Nakatsu, realized the kingfisher faced a really similar aerodynamic challenge when diving from low-resistance air into high-resistance water. By mimicking the shape of the kingfisher's beak for the nose of the train, a brilliant solution was born. The new train didn't just solve the noise problem, it was actually faster and consumed less electricity. Talk about a win-win. And this brilliantly illustrates how the concept applies to our grandest structures too. Take the architecture of Santiago Calatrava, specifically the Museum of Tomorrow and the Turning Torso. Calatrava isn't just trying to make his buildings look cool. He studies the twisting, load-bearing structure of the human body and the organic lines of natural ecosystems. He takes the efficiency, the adaptability, and the fluid strength of natural bone structures and weaves them directly into the steel and concrete of his designs. Here's another breathtaking example from 2011, the Stuttgart University Research Pavilion. Researchers had a complex structural problem to solve, so they turned to the skeletal structure of a sea urchin. By using computational design and robotic fabrication to mimic the sea urchin's geometry, they managed to build an incredibly light, modular pavilion capable of bearing massive loads. And the most staggering part of the whole shebang, it was built using ultra-thin sheets of plywood, just 6.5 millimeters thick. No way, right? If you need some hard science to prove that bio-inspired design yields massive quantifiable upgrades, Just look at these performance metrics. The silk of the Darwin's bark spider, it has a toughness 45 times greater than high-strength steel. When engineers mimic the structural colors and microscopic scales of butterfly wings, solar panel light absorption can increase by up to 200%. And get this, by putting the bumps called tubercles found on the fins of humpback whales onto the blades of wind turbines, we see a 30% reduction in drag and a 20% increase in energy generated.
Now for Section 4, Levels of Application. Let's see how this builds, because there are generally 3 levels of biomimicry. Level 1 is form and function. This is basically visual imitation. Think of Velcro, which was famously inspired by the tiny hooks on burdock seeds that stick to your clothes. Level 2 gets a bit deeper, imitating biological processes. This isn't about how things look, but how they're actually made, like figuring out how to manufacture synthetic spider silk in a lab without the spiders. Finally, Level 3 is the ecosystem. This is the absolute peak, where we look at how whole natural systems work together to create zero-waste circular human economies. It's like designing entire cities that function as efficiently as a mature forest. Moving on to Section 5, Innovation Methods. So, how do we actually do this? Well, there are 2 main directional workflows when looking to nature. The first is the top-down or problem-based approach. This is where you start with a human engineering problem, like a super noisy train, and you go searching through nature to find the analog. The second is the bottom-up or solution-based approach. This is where you observe a fascinating biological phenomenon first, like those hooks on a seed, and then realize, hey, there's a massive technological application for this. A very common framework engineers use is the biomimicry innovation method, or BIM. It flows in 4 sequential steps. Step 1, identify your human design problem. Step 2, biologize the question, meaning ask how nature achieves the specific function. Step 3, find nature's best practices by scouring those 11 million species for the absolute best champions. And finally, Step 4, generate ideas to translate that biological strategy into a manufactured product or process. And finally, Section 6, the bio-inspired future. So the crucial point we need to remember is that true biomimetics requires radical interdisciplinary collaboration. It's definitely not just for biologists anymore. We're seeing incredible advances where biology meets materials engineering and acoustics. For instance, researchers have actually developed biodegradable noise-reducing composites by studying the non-smooth microstructures of owl feathers and water insects. However, as we look to the future, we also have to recognize biological limitations. Not every biological solution can be universally copy-pasted to every technological context. We've always looked at nature with a sense of wonder, but biomimetics demands we look at it with curiosity and purpose. Nature is the ultimate mentor. It's spent billions of years running trial and error experiments, so we frankly don't have to. So I'll leave you with this one final thought. If nature has 11 million blueprints waiting out there right now, what will you learn to build next?